The last section that we're covering is 11.5, which is about the binomial theorem. Now, I've underlined here the bi. A binomial is just a polynomial with two terms. So a generic version I could write as just a plus b. Two terms added together. Examples of binomials. I could have something like x plus 3. That's a sum of two terms. One term is my variable x. One term is a number 3. I could have 3x plus 2y. That would be a binomial with two variables. I could have x squared plus 5x. That's a sum of two terms. This term just happens to have a second power. Still, though, a sum of two terms. I could have something like x squared minus 3x. That counts. I'm going to view that as a sum, though. So I'm going to view that as x squared plus a negative 3x. So I'm going to always view a binomial as a sum of two terms. If I have a subtraction problem, I'm just going to view that as adding the opposite term. And so that way I can have either a sum or a difference of two terms, but I'll always interpret it as the sum. Now, what the binomial theorem does for us is it gives us a shortcut for evaluating powers of a binomial. So a plus b to the first, well, I don't really need a shortcut for that. That's just a plus b. A plus b squared. Here I need to remember that exponents do not distribute over addition. So that's not a squared plus b squared. That is two factors of a plus b multiplied out. Now, I've written the first factor in black and the second factor in red. There is no difference between the black a plus b and the red a plus b. I'm just doing this so that as I work this out, I can keep track of where the different factors that I have come from. Because without a shortcut, I would just FOIL this out. So my first terms would be a times a. That's the black a times the red a. My outsides would be a times b. That's the black a times the red b. Plus, my insides would be b times a. That's the black b times the red a. Plus, my last terms are b squared. Notice that's the black b times the red b. Of course, usually when I FOIL this out, I then consolidate. I say that's a squared. These two things are actually the same. A times b and b times a are the same. So I've got two copies of ab plus b squared. Okay, FOILing that out doesn't take too long, but it starts to get more time consuming as I get to higher and higher powers. So if I have a plus b cubed, that's going to mean I have three factors of a plus b. Now again, I'm just going to color code. So I've got the black factor, the red factor, and the purple factor. Okay, and now what I need to do is distribute everything. Now, I've already multiplied out these first two factors. So what I need to do then is distribute the purple a to each of these terms that I have in the product of the first two a plus b's multiplied together, and then I need to distribute the purple b. Okay, so let's see if we can write this out. This is always mildly amusing. Okay, so I'm going to take these terms and I'm going to distribute the purple a first. So I'm going to have black a, red a, purple a, plus black a, red b, purple a, plus black b, red a, purple a, plus black b, red b, purple a. So these four terms are what I get when I distribute the a to this product, where this product I've got written in the line above. Now I've got to distribute the purple b. So I'm going to get each of these four terms multiplied by a purple b. I'm going to just move to the next line. So I'm going to have black a, red a, purple b, plus black a, red b, purple B, plus black A, red A, purple B, plus black B, red B, purple B. Oh my goodness. Okay, so now let's just see if we can't consolidate our terms. Okay. So if I take a look at this, that's all three A's. That's an A cubed. And if I look, that's the only one of these terms where I had all three A's. So I've got one copy of A cubed. Now this next term, that's two A's and a B. So that's going to be an A squared B. Okay. Well, that's also two A's and a B. And that's also two A's and a B. So it looks like I've got three copies of A squared B. Now if I look at my next term, that's one A and two B's. So that's an AB squared. Okay. Well, that's also one A and two B's. And that's one A and two B's. So I've got three copies of AB squared, and that accounts for all of the terms except for this last one, which was all B's, so that's a B cubed. Okay, now if I were to do A plus B to the fourth, I would probably lose my mind trying to color code it, okay, but I'd have to multiply out by a fourth factor of A plus B. What I want to do instead is see if we can look for a pattern, because the binomial theorem is going to encode a couple of patterns that are there. Okay. If I take a look, when I had A plus B squared, and I got all of these terms, notice every term was a product of two factors, one black, one red. So either the A or the B from this factor times either the A or the B from this factor. Now if I look at what I got when I did A plus B cubed, every single one of the terms that I got was a product of three factors. And they were all either the A or the B from the black, times either the A or the B from the red, times either the A or the B from the purple, until we had every possible combination. But if you look, all of those are a product of three factors. One of them's black, one of them's red, one of them's purple. Okay. And that makes sense because what we're doing is we're distributing each of these terms to each of these terms to each of these terms. Okay. So I can be highly suspicious that if I get A plus B to the fourth, I'm going to get a bunch of terms. Let's just make an educated guess here. I'm going to guess that I'm going to have a bunch of terms, each of which contains four factors that are either an A or a B. So if I have A plus B to the fourth, I could have, now this is just sort of my educated guess, I could have a term where all four factors are A. That would mean I'd have an A to the fourth. Let's see. If I had one less A, then I'd only have three A's. The fourth factor would have to be a B. So I could have some terms that are A cubed B to the first. Not absolutely necessary to write that exponent of 1, but I kind of like seeing it because then I can say, oh, the exponents add to 4. I've got 4 factors. I could have some terms where I've got one less A, but then I've got to have one more B because I've always got to have 4 factors. So I could have some A squareds, B squareds, plus some terms where if I had one less A and one more B, it would be an A to the first B cubed. And I could have some where I don't have any A's, but it's just a B to the fourth. Seems reasonable to me that these are the types of terms I should have. So if it's a binomial to the fourth power, I start with all 4 factors being A, and then for the types of terms I have, I systematically go one less A, one more B, until I've got all 4 factors are B. And it turns out that's right. Those are the types of terms we're going to get. And so then it just becomes a question of how do I fill in these blanks? What are these coefficients going to be? Well, one way to figure that out is to actually multiply it out. The binomial theorem gives us a nifty shortcut. And that shortcut, one way of dealing with it, is called Pascal's triangle. Now for Pascal's triangle, what I do is I start with 1, 1. Remember, we said a plus b to the first was a plus b. That's 1a plus 1b. So I start with the coefficients that I have for the terms that I get in the first power. To form a triangle, I'm going to come out like so and put some 1s. Then in the middle, what I do is if there are two numbers above a spot, I add them together. So I get 1, 2, 1. Now if you remember, when we looked at a plus b squared, that was a squared plus 2ab plus b squared. The coefficients were 1 copy of a squared, 2 copies of ab, and 1 copy of b squared. Kind of cool. To get to the third row, again, I just come out so that I'm forming this triangular shape, and then anytime there are two numbers in the row above, I add them. So 1 plus 2 would be 3, 2 plus 1 would be 3. I get 1, 3, 3, 1. Now, it's erased, but a plus b cubed, if you look back, it was a cubed plus 3a squared b plus 3ab squared plus b cubed. The coefficients were 1, 3, 3, 1. The fourth row of Pascal's triangle is going to give me the coefficients for these terms. So I go out like so, then 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. So my coefficients, I can now fill in these blanks. It's 1, 4, 6, 4, 1. Now, that's kind of cool. I gave you an informal suggestion of why it's right that these are the types of terms that we get. Because really, when we're multiplying binomials to certain powers, we are just doing a whole bunch of distribution. Okay? So that was just continuing a pattern that we noticed in the first three powers. I don't have a nice, easy explanation for why Pascal's triangle works. I wish I did, because I like to understand why things work. But to prove why this works is so much more complicated than just using it. And we really don't have time for that at this point in the semester. So I'm going to give this to you as a very, very nifty tool that you can use to get the coefficients, and just acknowledge we're going to have to accept this one as a gift from the mathematicians that have gone before that's true, but the explanation for why it works is beyond the scope of what we can handle at this point. Okay. All right, that's the binomial theorem. So what we'll do in the next few videos is just practice using it to evaluate powers of binomials.